the end of the week. I'm gone on Thursday for the grade 10 retreat. And then Monday and Tuesday, I'm also gone for a reading conference, which I'm really looking forward to. Okay, so here we have a function, okay, a piecewise function. So if you have a piecewise function like this one, and you're asked to find something like, here I'm asked to find the limit as x approaches negative 2. Okay, so in order for the limit to even exist, what has to happen? For a limit to exist, what has to be true? The right and the left have to be the same. Okay, so we need to check, in this case, where we're looking at negative 2, we need to check that the left limit and the right limit are equal to each other. So if I'm trying to do this, I would look at the left limit of negative 2, okay, from the left of f of x. Okay, and if I'm looking at the left limit, which of these three pieces of my piecewise function should I be looking at? The top one, the middle one, or the bottom one? If I'm looking at the left of negative 2. The top. Okay, so that's the one that's less than negative 2. Okay, that means left. Like, you could draw this out if you needed to, but drawing it out is probably not the easiest way. The easiest way is just to take a look at all the domains and identify which one would be left of negative 2. So less than or equal to negative 2 is the one that would be to the left of negative 2. And then all I do is I plug negative 2 into that. So I plug negative 2 plus 3, which is 7. Okay, so my left limit is 7. And then I do the same thing, but for the right limit. Ooh, whoops. Negative 2 from the right of f of x. And so which function will I use, which piece, will I use for right of negative 2? Not the bottom. It would be this piece here. Okay? So the reason it's not the bottom, like the bottom is also would be to the right of negative 2, but it's not going to be the piece that's closest on the right. It's like we're going to have this piece, the negative x, the top one, we're going to have negative x plus 3 until we get to negative 2, and then on the other side of that is going to be negative x squared plus 5x. Okay, so I should always try to identify it in the domain. So if it's left, I'm looking for the part where x is less than negative 2, and if it's right, I'm looking at x is greater than negative 2. Okay, so greater than negative 2 is that piece negative x squared plus 5x, so I plug negative 2 into that, so I have negative 2 squared plus 5 times negative 2. This definitely isn't going to be 7. I can just tell. Okay, so it's negative 4 minus 10 is negative 14. So they are not equal. So the limit, the actual value of the limit, does not exist. Okay, since they aren't equal. Okay, what that would mean is that graph would not be connected at that point. I would have one piece kind of up going wherever, and then the other piece starting at a totally different point. Okay, so the left and the right are not equal, so it doesn't exist. Okay, now B.
Excuse the interruption, but all students whose last names start with the letters Q, R, and S, please go to the drama room. That's all students whose last names start with the letters Q, R, and S. Please go to the drama room. Remind you, you do not have to buy a copy, but you do have to have your picture taken.
Just to remind you. Okay. So B, if we're looking at B, and we want to look at x approaches 3, if we're looking at that value instead, okay, I should be looking at, here, I might just cover this up. B, for 3, I'm going to make this bigger. It's not letting me. Sad. That's exciting. Okay. Anyway, for B, left of 3 and right of 3. So if I'm looking at the left of 3, that means I should be looking for where x is less than 3. So which of the three functions has x is less than 3? The middle one. Because right there, x is less than 3. So I just plug it in, f of x. So I just plug in 3 into there, so it's negative 3 squared plus 5 times 3. So it's 15 minus 9, which is 6. Okay, and then I do the same thing, but from the right. And if I'm looking at the right, I should be looking for the function that has x is greater than 3, which is obviously the last one. Okay, so I just plug in 3 into that, 3 minus 2, which is 1, which also, so this one also does not exist. Okay, so the only way you would end up with the limit existing is if the left and the right limits were equal. Okay, so they're not in either case. So that means in both situations, like what would be happening here is we'd end up with a graph, like, the first graph maybe looks like this, and then our second graph, it starts like down here and is like this, and then our third graph starts somewhere up here again and goes up that way. And so our three pieces of our graph are just like not going to be connected to each other. Okay, there's not going to be any points. So at all these spaces in between, our limits don't exist. Okay, that's sort of what's happening. It's a little tricky. Okay, so let's look at some other problems. That's how you do piecewise functions, though. So hopefully everyone I know I showed one. Now this question in particular, and some people had to go get the pictures taken. They're going to be really bummed out. This question is on the worksheet, the assignment that I gave out on whatever day that was, Friday. Okay, so this exact question is on it. This is how you should do it. So this is a question. They want us to find the limit as x approaches infinity of sine x over x. Okay, so the limit as x approaches infinity. Oh my god, that is crazy.
Laura, are you okay?
Yeah. Do you need to go get some water?
Yeah, go. Don't make me sick.
I don't think she can make you sick from there. Okay? So we are looking at the limit as x approaches infinity of sine x over x. Okay, the way that we would do this one is using the sandwich theorem. Okay, so putting sine x over x in the middle. And we learned this the other day. So the sandwich theorem is that thing where it's like if you have a is less than b is less than c, and then you can show that a and c are the same, then it proves that b is also the same. That's the theorem we learned last week. Okay, so if I have sine x over x, okay, does anyone remember what I said? Sine x must always be greater than. No. No. -1 is the answer. Okay? She is trying. So sine x over x then must be greater than -1 over x. Okay, it's the same thing. It's the -1 goes on top because that's the part that sine x is less than. And then it must be less than -1 over x. And on the other side, okay, sine x must be less than 1, so it must be less than 1 over x. Okay, so if we take the limit of each of these things, and if we take the limit as x approaches infinity of that one, and of this one, and I guess of the middle one as well, if I'm taking the limit of all of these three, now the middle one I don't know, but these ones on the outside I can do, because if x is approaching infinity, what will I get if I have 1 over infinity? What will that be equal to? 0. Okay, because if you have any number over infinity, like any normal number over infinity, even if it's a really high number, like even if I'm like a bajillion over infinity, okay, that's still 0. Infinity is so big that if we're dividing any number by it, no matter how huge, okay, we are still going to be getting a 0, okay, as a limit. So it's 0 on that side, so we'd say the limit of x approaches infinity of sine x over x is less than, and on this side it's the exact same thing, it's also 0. So we can state with some certainty that the limit that x approaches infinity of sine x over x is 0. Okay, so remember the concept here is that if I tell you, like this means it's between 0 and 0. Well, if it's between 0 and 0, it must be 0. There's no other numbers that are between 0 and 0. Okay? That's the concept of the sandwich theorem. So this is another one. As I said, it's on your sheet. It's on the assignment. It's another one that you might want to memorize. So remember, we also have that we should memorize separate from this question. Oops, oh God. The pen is just being super jumpy today. Okay, Why is it doing that? Okay. We also have that limit as x approaches 0 of sine x over x. Does anyone remember what that one's equal to? 1. Okay, you're supposed to have that memorized. Okay, so you can memorize that. And also, if you want to memorize this one, you certainly can. You could also prove it quite easily, but it's maybe better to memorize it, that the limit of x approaches infinity of sine x over x is 0. Of course, it's easy to mix them up. So you have to remember which is which. Okay, now these are just the same rules as before, so I'm not really going to go over them, but just to state that they do, like just the way that they apply to other limits, they also apply to limits as approach infinity. So it's the same thing though, right? It's like if you have two limits that are adding, you can add them. If you have two that are subtracting, you can subtract them. There's nothing weird. Okay, so when you have one like this, and in fact, whenever you have a fraction, okay, and you have a fraction like this one here, or any fraction at all where there's just one term on the bottom, but there's multiple terms on top, your first step should be to split it into two different divisions. Okay, so this is equivalent to the limit as x approaches infinity of 5x over x plus sine x over x. Like they're equivalent to each other. Because all that top fraction means, right, is that I'm dividing both terms by x. So I can split it up. So whenever you see a fraction, you can't do this the opposite way, by the way. Like if you have more than one term on the bottom, you can't split it that way. I'll show you what I mean in a minute. I'll show you an example. But as long as you only have one term on the bottom, you should do this. Because then we can simplify it a little bit more. Or, you know, whatever, you can do it however you like. But x and x can cancel there. So the first part of that limit is equal to what? 5. And then I know, because I just learned it, that the limit as x approaches infinity of sine x over x is 0. So this is just 5 plus 0, which is 5. Okay, which is actually a really easy question. Okay, so, but if you didn't split up the fraction, if you left it as a whole thing, it would be hard. Okay, so you need to know that you split those. Just the example of like an anti-example, I guess. What not to do. Don't do this. It's not allowed. If you have something like x over x plus 2, that is not equal to, I can't stress this enough, it is not equal to x over x and x over 2. Okay, they are not equal to each other. Okay, it's a different situation. You can't do that, so please don't. Okay? Do not do that. Do not. It is wrong. Okay? But you can split it up the other way. Okay, so is that one easy? Does everyone understand it? It's fine. Okay. Okay, this is a slide we saw the other day. End behavior model. So end behavior models, it's just something we call, and honestly, I don't really test on this, but a right end behavior model is if on the right it's approaching 1, like if you look to the right of the graph, when it's going to positive infinity, the graph is approaching 1, and it's left if, as you go to the left, okay, the negative infinity if it's approaching 1. So it's like if it has a horizontal asymptote of 1 on either side. If it has both, we just call it an end behavior model. So I'll just show you kind of like a drawing of them so you can understand kind of what I mean. But if you had a right, it could look like, okay, like that. And that is at 1. Okay, 1. Okay, at left would be the same thing, but on the other side. So you have some kind of graph that's like, woo, and its asymptote is at 1. Okay, and just both would be like if you had something like that, where on both sides it's going to 1. Okay, so that's just it's just like a name. I don't know why it matters, to be honest. But it's like what we call it, so you should know it. Here, so this is an example. They gave us a function, f of x, x plus e to the power of negative x. Remember, e is just a number. We talked about that during the pre-calculus. So e is just like pi. It's on your calculator. Like, it's just a number. It's 2.71, blah, blah, blah. So please, when you see e, don't panic. It's just like any other number. It's a constant. Now, they want us to show that g of x equals x is a right end behavior model, and that h of x equals e to the negative x is a left end behavior model. So to tell if it's a right end behavior model, what I do is I take the limit, and because it's right, what I remember is it's going to the right, so that's going towards infinity, of x plus e to the negative x divided by x, because that's what g is here, equals, and I just calculate it. So what I do is I split this fraction just like I split the other one. I split it down the middle. So I do x divided by x, and maybe I'll write it out so that everybody can see exactly what I'm doing, but I do x divided by x plus e to the negative x over x, like that. Okay, so, and that should be, sorry, I'm still taking the limit at that point of infinity. So if I plug, actually I should just do my simplifications first. Like x over x simplifies to what? 1. Now on the bottom here, if I plug in infinity, okay, if I plug infinity into this, okay, so imagine I plug infinity into the x up there and the x down here. So I have e to the power of negative infinity. This stuff is stuff that some people are good at and some are bad at. If you take something to the power of negative infinity, will it be a big number or a small number? Very small, okay? Negative infinity is like, taking something to the power of negative infinity is going to be like 1 over e to the power of whatever. So it's going to be basically 0. And on the bottom I have infinity, so it's going to be 0. So it's 1 plus 0, which is 1. Now, say you didn't know that or you were having trouble figuring that out because it's a little weird to think about. You're like, I mean, if you had your calculator, if it was just on an assignment, you could, of course, try it out. Like, try e to the power of negative 50 and see what it does. It's going to make it very small. But if you couldn't do that, I mean, in this example, they tell us that g of x is a right end behavior model. So that means that it should equal 1. Like, so we should kind of be able to guess that it's going to be 0, even if we didn't know it was going to be 0. Now, if we do the same thing but with the left behavior model, so x approaches negative infinity, okay, of f of x, so x plus e to the negative x over e to the negative x, okay, equals, okay, now I have the limit of x approaches negative infinity of x over e to the negative x plus e to the negative x over e to the negative x, which is just 1. Oops. Okay, so that one, I know the second part of that is 1. So the second part's easier there. Now the first part, x over e to the negative x, now I'm putting negative infinity into there. So it's a little weird because it's going to be negative infinity, like e to the negative infinity, which is e to the positive infinity. So if I took something and put infinity in the exponent, would it be big or small? No, it'd be big. No. Okay, so anything to the power of infinity is going to be a very large number. So it's a very large number on the bottom, and it's negative infinity on the top. But this is actually one of those situations where we have one infinity is bigger than the other. So kind of let's talk about it a little bit. So what we end up with, right, if we have x over e to the negative x, and we plug negative infinity into both. I have negative infinity over e to the negative infinity, which is negative infinity over e to the infinity. And what we end up with is kind of a weird situation where we have infinity on both the top and the bottom, because e to the infinity is definitely infinity, and negative infinity is also infinity. Exponential infinity is a much larger infinity than just regular infinity. You can tell, like, if you took any kind of graph, like if I just took a graph x and a graph e to the x, okay, what you would see, if that's x, e to the x might be under it for a long time, but eventually it goes straight up. Like, it goes really far up, because that's what exponential is. Exponential grows at like an extremely fast pace. So it's sort of something you just have to remember. If you have something like 6 to the power of x and you're looking at x being infinity, that is huge. This is like a really big, and you don't end up with situations very often like this, but when you do, you want to recognize that this would be higher. So we end up with the infinity on the bottom. Basically what that means is that the infinity on the top becomes insignificant, and this becomes 0. Okay, because we have a number divided by infinity. And I know that's weird. I know it's weird, but maybe I can find some good videos about infinities. Okay, so it's 1. Okay, so that there are, if you have infinity in the exponent, just so you know, if you have infinity in the exponent, that's going to be a higher infinity than like a polynomial type. Okay, so that's something you can kind of memorize. If you're curious about more, I will look for some information on it for you. Okay, so let's look. Okay, this is a situation that actually I think there's a question on the test where you're supposed to use it. I'm trying to remember, I just feel like last year Sarah Hart was like the only person who figured it out, but it was like a hard question. So this is something that you can use in like really specific situations. Sometimes if you're like given an equation and you can't figure out what to do with it and x is approaching infinity, something you can do is you can switch x for 1 over x, and then let x approach 0 instead. Okay? It's kind of a weird rule. So you think about it, the reason it works is because if x is approaching infinity, and then we take 1 over x, well, if x is going to infinity, this whole thing then would be 0, right? So it's like we're switching it, and we're letting x approach 0 instead. So I'll show you how it actually works. Okay, so it's like in this situation, if I was given this graph, limit as x approaches infinity, I wouldn't really know what to do with it necessarily. And I'd be like, oh, I'm not really sure of the answer. But what you can do is you can replace x with 1 over x. So if I do that, I have sine 1 over x. And then I can switch the limit to 0 instead. Okay? Now, what is 1 over x? Does anyone know? What's a simpler way to write that? Nobody? Let's try it out. 1 divided by 1 over x. Does anyone remember the rule for dividing a fraction? Multiply by the reciprocal. So it's x. So I can look at this as the limit as x approaches 0 of sine x, which is 0, because I can just plug 0 in. Okay? So this is like a really specific situation. It comes up pretty rarely, but sometimes if you're given, and honestly I think it might be this exact problem is given on the test, but it's like if you're given something where it's approaching infinity and you don't know how to deal with it, then you can try this out. You can let x be 1 over x, and then simplify it and see if you can plug it in more easily. Okay, this is 0 because if you plug 0 into sine x, it gives you 0. Okay, so that's why. Okay, so it's just like a really specific situation. Okay, we're going to do just a very basic discussion about continuity here, starting to talk about continuity. I've been talking about it a little bit already. And then we're going to have some time to work. I know it's been a while. Okay, so a function, we call it continuous at an interior point if, and this is really an important definition because I find students forget this definition, is that, so put a star next to it or something, it's important to actually know that the limit of x approaches a of f of x is equal to f of a. A less formal version of continuity, and this is what most students say. Like, I get it on tests all the time. I'm like, prove that this is continuous, and I get students explain it like as if they were talking to a child or something. I would like to see this definition. If I'm asking you to prove that something is continuous, I want you to use this definition. What I don't want you to do is say what I'm about to say to you. I'm explaining this to you so you actually understand what continuous means. Continuous means that you could draw the graph over that interval without picking up your pencil. That's what continuous means. Okay? That you could trace the entire graph without picking up your pencil. So for instance, if I have a graph and it's like from A to B, and I can draw it and it's like this, that's continuous because I drew that without picking up my stylus and having to do anything weird. Now, if I have one from A to B, and it's like, that is not continuous, because I could not draw that without picking up my stylus. Okay? If you have one like this, that's not continuous, because I can't jump over that little hole without picking up my pencil from the paper. Okay, so this is not continuous, continuous. Okay, now that is an informal understanding of continuous. It works all the time. Okay, it's always true. But if I'm asking you to show that something's continuous, the way you show it is by saying that the limit at that point is equal to the function at that point. That's what this actually means. This, right? We're saying that the limit is equal to what you get if you just plug the value into the function. Okay? So an endpoint, a function f is continuous at endpoints if it's a endpoint on the left, if the right limit is equal, and if on the left it's that the right limit is equal. So just sort of making a rule for the endpoints. So like here, all I would care about is the right limit. Yeah, I wouldn't care about the left limit because there is no left limit. Okay, so that's continuity. Let's kind of see an example here. Okay, so if I'm looking at this graph, okay, it wants us to know where is f continuous and what are the points at which it's discontinuous. So if I'm looking for where it's continuous, I would write it in interval notation. That's weird. Continuous, I would write it in interval notation. So this one is continuous because I can start here at 0 and I can keep drawing until here without picking up my pen. Does that make sense? That piece is continuous. So I can say it's continuous from 0 to 1. Okay, now notice even though at 1 there's an open circle, I can still say it's continuous at that endpoint because the left limit at that endpoint would still exist. Okay, and it would be equal. Oh, actually, it wouldn't be equal to the function, would it? So I shouldn't say that. Okay, sorry. So because here, the left limit, I'm glad I talked about that. Okay, the left limit of that function is 1, but the function at 1 is what? What's the function of this graph equal to at 1? 1. Oh, sorry, this should have been 0 here. 1. Okay, it is 1. So the actual function here is 1, but the limit is 0. Okay, so since those aren't equal, I can't include it in my continuity. Now, if I go to the next piece of the graph, I can trace from 1 to 2. Okay, so I can go from 1 to 2, and it includes 1, but doesn't include 2. Okay, then from there, but I can't count 2, right, because there's an open circle there. That open circle is a point of discontinuity. Then from 2, I can go all the way to 4. Okay, and it doesn't include 2 again. So from 2 to 4, should I include 4? Should I put hard brackets around it? Yes, because it's a circle. Okay, so that's the places of intervals of continuity. On the first one? Because down here...
Interruption, would all students whose last names start with the letters T, U, and V, please go to the drama room. That's T, U, and V to the drama room.
Because down here at 1, it's an open circle. Okay?
Oh, is it? Okay.
Yeah. Okay, so that's the continuity. Points of discontinuity, you would just say, if you were asked for we are here, I guess. So we should do it. Points of discontinuity, you could just list them. You just list them as like x equals 1, 2, and that's it, 1 and 2. Because that's the places where you'd have to lift your pencil. Okay, those are points of discontinuity. Okay, it's pretty, so if you're just asked like this, you don't need to explain formally, but if I say show the graph is discontinuous or show the graph is continuous, you need to use the formal definition. Okay, so here, this one is a function you're going to see from time to time. There is buttons on your calculator for it. I wonder if I can find it right away. Yeah, if you go math num, it's the fifth option. Okay, if you go math num, it's the fifth option. This y equals int x. Basically what it is it stands for integer. So here, if x is between 0 and 1, the integer value is 0. If x is between 1 and 2, if it's here, it's 1. If it's between 2 and 3, it's 2. If it's between 3 and 4, whatever. Okay. So it's math. If you hit the math button, go over to num. It's the fifth option. So you can actually graph this on your calculator. Okay. So here, where do we have points of discontinuity? How would you describe these points of discontinuity to somebody? They happen a lot, right? They happen every time we have a jump. Okay, each one of those. What would we call those numbers? What are those numbers? It looks like -1, 0, 1, 2, 3, 4. I imagine it continues on either direction. Integers. Okay, so the way we would write that there's a point of discontinuity at every value x equals n, or any other letter you want, where n is an integer. Does anyone know the letter that represents the integers? It is not obvious, by the way. It's not I. I said it's not obvious. I is actually not the letter that we use for integers. I mean, if you saw I used, it would be like, okay, somebody used the wrong letter. But like you'd probably know what it meant. Anybody know?
Q.
No, that's rational numbers. That's a good guess, though.
Z.
It is Z.
Sorry, bonus points for that?
Yes. Yeah, bonus points for Haley. Everyone keep it in mind the rest of the year. Okay? Okay? It is a Z, means integers. Okay? If you used I'd mark it right, even though it's incorrect. Okay. So we would say that here it's every integer value, and I don't know, writing the points of continuity would take, you'd have to write something similar. You'd have to write something like, I don't know, like it would be ugly, to be honest. I'm not really sure how you'd write something like, you could write x, you could write like x is between, if we're doing continuity. I would never expect you to do this, by the way, but it would be something like x is greater than or less than n, and less than n plus 1 for any z. Okay, that would work, because we're saying that it has, like n could be any integer, so like 0, and it's going to be between 0 and 1, we're fine, but then once we get to 1, it's not going to be fine anymore. But it's pretty ugly. So every time there's a jump, there's a thing. This is just the first time you're seeing this integer function again, once or twice, not a lot. Now this slide, you have to memorize these. They're not that hard to memorize, though. I don't know, like students, like you should know them for the test. There's at least 1 or 2 questions that are like, what type of discontinuity is this? And you should be able to tell, like just looking at the picture. Okay, so there's 4 types. There's the removable discontinuity, which is this first one. Okay, this first one here is removable. Okay, it's called removable because there's only one point that requires filling. So if I just filled that point somehow, I would remove the discontinuity. Okay, like it's like the only problem here is that I have to jump there. Okay, so that's called removable. Okay, if there's just a point to fill. The second one, unremovable. Okay, sometimes unremovable is just called jump. In fact, more often it's just called jump, but it means unremovable as well. If you called it jump, that would be fine. Is when you actually, like, you can't just remove it. There's not just a hole missing. It's like you'd have to jump from one place to another on the graph. Okay? Then infinite is obviously when one or both sides go to infinity. Okay? So just like you have to lift your pencil because you were going up to infinity. And then here, the last type is a weird type. It's called oscillating. Okay, so that's where you sometimes will graph things and will get really weird squigglies and they never ever connect, that is called oscillating. Okay? So oscillating means wave. So that's how you should know it. Okay, we're gonna have some time now